So what I'm going to do is I'm going to do a few problems today so that you can see how kind of how the theory works and how dealing with kinematics in 1D works. So for starters, I'm going to rewrite all of our kinematic equations, but now instead of using A, I'm going to use what I'm going to commonly work with from now on, which is A equals, anyone? Negative G. So for instance, if we're looking at the velocity formula, it would be Vf equals Vi minus Gt. If we're looking at the first kinematic equation, it would be delta x is equal to Vit minus Gt squared over 2. And the second kinematic, yes?
So are we now saying that the constant acceleration
is gravity. We're only dealing with free fall for pretty much from here on. These are going to be the basis of our questions going forward. And we have Vf squared minus Vi squared equals negative 2g delta x. And implicitly, what am I saying up is? Positive or negative? Positive, that's correct. Do I need to say that? Well, I mean, does it need to be positive? No. And it's important that you realize that. But the full appreciation of it won't come till later. Okay. So first question I want to answer is Chris's question, which is why, when I throw something up, or this was kind of the question that you had in your, so if I stand on top of this desk, and I were to throw up this marker, no. How about from right here? I throw up this marker. Okay. The question is, what is the velocity, or what is the velocity when it reaches my hand? Let me use the troll ball. All right, here's the troll ball. All right. In other words, on its way down, what was its velocity? At the same point. And the answer is it's exactly equal to the speed. If you neglect direction, the speed on its way down at that same point is equal to the speed with which it left at my hand. And yes? The velocity is the opposite, correct. And why does that happen? Where did that result come from? Well, it comes from the second kinematic equation. In other words, if I were to ask you, what is the total displacement when it reaches my hand? If I could catch. The total displacement is 0. So what happens here? What do you get? You get that Vf squared minus Vi squared is 0. Which means what? Well, one thing it means is that Vf squared equals Vi squared. And what's going to determine the direction? Basically, physical reality. If I were to actually formally solve this, how would I formally solve this? I would have to factor it. What's the factorization of this? So this is Vf plus Vi times Vf minus Vi. And what are its solutions? What's its solutions? If A times B equals 0, that implies that either A equals 0 or B equals 0. So what does this imply? This implies that Vf plus Vi equals 0 or Vf minus Vi equals 0. Which means that the two solutions are Vf equals negative Vi or Vf equals positive Vi. Which solution is not physically possible? Vf equals plus Vi. So we rule out that solution based upon physical reality. This is not a physically reasonable solution. So, other properties. If I were to ask you to calculate the travel time, how long is the travel time when I throw this up and catch it at the same position? How do I solve for the travel time? Well, there's a couple different ways to do this. Pick your poison. Which way do you want? Easy or hard? Easy. Neither of them are hard. Both of them are easy. So I'll do it both ways because they're both instructive. So one way is to use the definition of acceleration. Well, what's acceleration? That's right. So A equals delta V, right, over delta T. Therefore, delta T is equal to delta V over A, right? So, if this thing gets projected at a velocity vi, we have the following, that delta T is equal to Vf minus Vi, correct? What's A? Negative G. But what do we know about Vf in the case where the change in position is 0? That's what? It's negative Vi. However, since delta x equals 0, this implies that Vf equals negative Vi. Hence, what do we get? We get negative Vi minus Vi over negative G, which is equal to negative 2Vi over G, negative G, and I'll zoom out a little bit. And what do we end up with? That the change in time is 2Vi over G. So, a couple questions. Is this physically possible, yes or no? And by me saying is it physically possible, what am I really saying? Is T positive? And the answer is yes. Why? No, is this T positive? Is that T positive? Yes or no? And the answer is yes. Why? Because Vi is positive. Why is Vi positive? Because it's directed in what direction? Up. And what about G? Is G positive? The answer is yes. Why? Because I said G is the magnitude of the acceleration of gravity. So that is physically possible. It's great. So there you have it. That is the time it takes to have a zero displacement. So just so that you guys understand this, what that means is this. If I project this from the ground like this, the time it takes for it to reach back to the ground is 2Vi over G. Is this a formula, yes or no? And the answer is no. If you start formula hunting, guys, you'll be hunting all year. You need to be able to derive these things from first principles. And the first principle is delta x equals 0, right? Which means by the second kinematic equation, the final velocity is antisymmetric to the initial velocity. And hence, you can solve for the change in time. Another way to solve for the change in time is we can use the first kinematic equation. Just straight up. First kinematic equation says what? Delta x equals VIT plus minus 1/2 GT squared. Right? What is delta x? 0. Delta x is 0. What can I do? Yes? I wouldn't recommend it, but you're close. What can you do mathematically? I can factor out a t. And the reason why I wouldn't recommend it, Andrew, is because there is another solution. There is a slightly non-trivial solution associated with this. You'll see. Factor out t, what do you get? You get vi minus gt over 2, right? Equals 0. What does this imply? What are your two solutions? Vi minus gt over 2 equals 0, or t equals 0. I'll get back to this in a second. Solve for t here. What do you get? Anyone? T equals? Come on. 2vi over g. In other words, it's completely consistent with the other solution. Which was easier? They're both easy. But you did get an additional solution here that's kind of interesting. What was the other solution? T equals 0. Is that a physically reasonable solution? Yes or no? Yes. What does that correspond to? Yes. That's right. It's the initial starting point. Exactly. So you guys are good. Now I suspected it. You guys are pretty heavy hitters. A lot of smart kids here. So now I'm going to do a problem that I actually didn't include. I actually included it originally in your homework, but then I figured I'd have mercy on you. So, that's not really true. The truth of the matter is that this is too good of an example for me to pass up. So, here's the problem. A stone is thrown upward with a speed of 10 meters per second from the edge of a 120-meter high cliff. Find everything. And you'll see this is kind of my style. Like I'll say find everything. All right, meaning like everything there is to find it. Well, 10 meters per second is, be careful. The acceleration of gravity is approximately 10 meters per second squared. What does that mean? That means an object is, that's correct. You might want to write that down because this is a good mnemonic. It's a good way to think about acceleration. That for every second, an object is increasing its speed by 10 meters per second, assuming that it's not changing direction. If it's moving in one direction, let's say straight down. All right. So what do you have? You have what's the situation here? It's a 120-meter high cliff, and you throw the ball up 10 meters per second. So what do I do? What's the first thing I do? Come on now. We're all pros here. You draw a picture. That's right. And implicitly, what does that mean? What do I really do? I establish. We're past that point. That's what you do in. And that would be an insult to you guys. When you start off a physics problem, you establish your coordinate system. So let's establish our coordinate system. And what does it mean to establish my coordinate system? Set an origin. Where am I going to put the origin? You sure? You sure? Oh, all right, let's do it at the ground. So this isn't fair. I can't guess what's in your crazy head, Khalil. I mean, seriously. So, which way do you want to call up? Positive. So then what's the top of the cliff? It's positive 120. Beautiful. Absolutely beautiful. So here's this guy. He has nothing better to do. He looks down because he's scared. And he throws this ball directly upward. 10 meters per second. The key to almost all kinematics problems is time. So let's solve for it. How can I solve for it? First kinematic equation. So first kinematic equation says what? I can't hear you. Huh? I can't hear you. VIT minus GT squared over 2. All right? And I'll even throw you a bone. G is 10. So, what's VI? 10. So, what do? What's delta X? Yes.
Since that changes to meters per second for the acceleration of gravity,
10 meters per second squared.
right, would that mean that after 1 second it would be 0?
Ooh, you're a sharp one. Very nice. Yes, that's very good. Very, very good. So, she said after 1 second it would be at rest. She's right. It's not obvious. But let's actually solve this. So, what's the displacement? Mm-hmm. You sure? Well, how do you find displacement? Casey's looking at it like, I think I know it. I think I know. What are you thinking? No. This guy is infinitesimally tall. He's like a 4-year-old. All right? He's infinitesimally tall. So, it means that he has no, don't worry about his height. Don't take that into account. He's at 120 meters. So, what's the displacement? You sure? Well, this is when you tell me, Khalil, no, stop this. I can't infer this. I need definitions. What's the definition of displacement? What does delta x mean? Change in position. What does that mean? No. Change in position means final position minus initial position. What's the final position? 0, right? So this is xf minus xi. So it's 0, right, minus the initial position, which is 120. Notice the displacement is positive or negative. Why is it negative? Because it went down. That's right. It went down. So, carry it all over to one side. You get 5t squared minus 10t minus 120 equals 0. Factor out a 5. You get t squared minus 2t minus 24 equals 0. Factor that. What do you get? T minus 6, t plus 4. What are your solutions? T equals 6. T equals negative 4, which is physically unreasonable. Negative 4, so this is your proper solution. We will return back to that negative 4 seconds. Because in physics, nothing is totally useless. All right. So we have the time. Now what? Now that we have the time, we can find other things. What else do you want me to find, Khalil? You want me to find the speed just before it hits. How do I find the speed? I can use the definition of acceleration or a rearrangement. In other words, VF, right, equals VI minus GT. What is the time? 6 seconds. So we get VF equals 10 minus G was 10, so this is 10 times 6, and we get VF is negative 50. What's the speed? 50. Mr. Cleel, there's no units. Now there's units. Now, what distance did it travel? Oh, what distance did it travel? Clearly, it traveled that 120, but it traveled a little bit more. So what do I need to find? Yes. That's right. I need to find the highest point. Because if I can find the highest position, right, then the distance would be that change in position, absolute value, that change in position, absolute value, plus 120. So how can I do that? Well, second kinematic equation. Why? At the highest point, what is the instantaneous velocity? 0. So we have VF squared minus VI squared equals negative 2 times 10 times delta x. But at top, VF is 0. So we have negative 10 squared equals negative 20 delta x, which means delta x is, by the way, that's not negative 10 squared. You guys all know how to read that. When you read that, what number do you see? That's negative 100. Why? Yes? Well, PEMDAS says what comes first? The exponent comes first. So that's 10 squared, then it's minus 10 squared. All right, it's negative 100. So what's delta x? 5. So what happened? This thing went 5 meters. Let me draw this. And of course, I'm going to draw this by zooming in to 50. You guys don't mind if I zoom in, do you? You can say, yes, we do. Won't change much because I'm kind of constrained here. But basically, this goes up to a position of 125 relative to the ground at 0, right? Goes up 5 meters. It comes down 5 meters. And then it goes down another 120. So the total distance is 130. Any questions? And what this shows you is that a good example is worth at least 100 words or so. All right. I could keep on doing this, but I'd rather go to Pear Deck. How do you guys feel? Would you like more problems? Chris?
I know it's going to contribute for our test next week.
Yes.
What's the format of it? Is it a lot of word problems?
Oh, okay. Okay, so did I go over this with you guys at all?
You said it was AP questions.
All right, so format of the test. So basically, this is how it goes. There's 2 pieces, free response and multiple choice. Free response should be about 15 minutes. I'm only going to start off giving you 1 free response question. In later exams, you're going to have 2 free response questions. Generally speaking, I start off, I think it'll be, what is 20 times 1 point? I need somebody to do this for me. 20 times 45 over 35 is? 25.7 plus 15 is 40.7. How many minutes are there in the class? So you're going to have basically 25 multiple choice, 1 free response. The 25 multiple choice and the free response comes from either released materials or released kind of materials. A released kind of material is the best approximation for a, I think that's mine, right?
I don't know.
Yeah, I believe so. For the AP exams, because realize how many years of AP1 exams do we have? Suitor! How would you describe the test in this class? There you go. So, thank you, man. Sure. I don't know what it is. Is that NHS? Let me guess, it's due tomorrow? Thanks for planting the seed, Jack. All right, so basically you're going to be under the gun the whole time. The whole time you're going to be under the gun. And anyone who's taken the AP exam before knows you're under time pressure. Did you run out of time? Yeah. All right, so the whole purpose of this is to prevent that from happening. So you're going to be under the gun, but the good thing is it's curved. And remember, what's your goal? Yeah, I'd say aim for that 70 mark. You're in good shape. All right? What that means is you've got to make decisions. You find yourself taking more than a couple minutes on those multiple choice, you skip it and move back. So, and that's a skill. I can't stress this enough. It's a skill that needs to be developed because it's hard to know when to cut your losses. Any questions?
I'm guessing the multiple choice would be like prompts or they more conceptual based.
They're special. That's all I can say is they're very, very, very well constructed problems, mostly conceptual. But a conceptual problem, as you've seen in this class, I'm sure you're getting your kind of real first taste of it. The real hard part of this class is the conceptualization. I don't know, is that true? Actually, I'm just going to open this up and oh no, actually I know what to do, because I already ditched the people who've left. So, or that's what. So, and let's switch views. Open projector view. Go 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 go. Go, 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 go. We'll get back to this problem. It's good, but we've got more things to worry about, like this. So I don't know if we're going to make it by Tuesday. I hope we are, but we're probably not. It might get moved to Wednesday, but it's definitely not going to be moved to next week. So, I mean, it's not going to be moved to the following week. It's going to happen by the end of the next week. So this is a motion diagram, moving along the x-axis with constant acceleration. The dots 1, 2, 3 show the position of an object at equal time intervals. So each of those objects happen at 1 second, 2 seconds, 3 seconds, so on and so forth. At the time label 3, what's the signs of the object's velocity and acceleration? 1 minute. I get these things wrong. Let's see. Oh, I should probably start this. 30 seconds. Oh, where's my laptop? Where'd you go? Maybe Anybody see a laptop around here?
Slowing down, so that means there's some kind of force.
Ooh, forces. My goodness. Someone's bringing in outside information into this class. No, you might be right. But I would just be careful because I don't think you know force is. Yep. All right. And let's see what the time says. Come on, Khalil, start this up. Let's see who's left. Almost everybody's responded. And anybody want to volunteer their minds? Time. Let's see what the distribution looks like. Almost everybody says E. So let's take a look. So clearly, which direction is it accelerating? To the right. Notice I didn't even say whether it's positive or negative yet. I know it's accelerating that way. Okay? What's happening to the velocity? The velocity, or the speed, is it's increasing in that direction, right? So, but turns out that direction is negative. So there you have it. Right? So, what does that mean? I think A is less than 0 and V is less than 0. Is that right? Right?
It's 0.3.
What's this?
It's 0.3. And that's positive.
Oh, yeah, that's right. That's right. I'm sorry. Thank you. Sorry about that. So, well, ooh, no, wait. No, wait. Wait a second. So, its position's positive, but its velocity's not necessarily positive. I mean, the way I interpret it is that this is at t equals 1, 2, 3, 4, 5, right?
Yes, I was looking at it 5, 4, 3, 2. I was just like,
I'm not a big fan of motion diagrams, but yeah, I mean, this makes sense to me. What'd you say? All right, so which ball has a greater acceleration? Looking at this. So Alice throws the ball downward. Bill simply drops it. Which has a greater acceleration just after the release? Ooh, excellent. "15 seconds. Oh my God, I hate physics. It's so amazing. Well, people get it wrong. People get it wrong, and it's incredible because you think, oh no, this is obvious from a teacher's perspective, and you have no idea what students are thinking. It's amazing. No, a lot of people get it right, but you think everybody should get this right. All right? So 5, 4, 3, 2, time. All right. The answer is the acceleration is the same. That's right. The acceleration is the same. Notice it's right after they release it. Right? After they release it. So what this question is really designed to do is make sure you compartmentalize velocity and acceleration. Although the ball that Alice throws starts off with a greater velocity, it's accelerating at the same rate as Bill's ball. Meaning that the rate with which velocity changes is the same. Turns out the reason is because both of them are acted on by the same force, which generates the same acceleration, namely that of gravity. So which one has a greater velocity when they hit the ground? Clearly, Alice's ball will have a greater velocity. Okay. If there's no air resistance, what do you expect the two speeds to be?
Where?
When they hit the ground. One throws it up with speed v, one throws it down with speed v. Know that this, when it hits the ground, be careful.
Wait, the magnitude.
Remember, we are in accelerated motion. So you have to think in terms of accelerated motion. Correct. Jack, Emily, Casey, Brian. Oh boy. Yeah, this is very interesting. All right, good. So now, lock those answers, show you the responses, and we've got not quite a consensus at all. So let's actually reason this out. What did we learn from today's lesson? That when Bill's ball gets to this point, what is its speed going to be? Yes.
Like the same magnitude?
But opposite direction, meaning it's going to be negative V0, right? Or V0 going down, which makes it identical to the initial conditions of Alice's ball, which tells you what? Since they're both going the same displacement, what can you say about, and they both have the same initial speed, what can you say about their final speeds? The same.
Just drop it?
No, she threw it
Okay.
with the velocity V0.
Okay. Yeah, that makes sense now.
Okay? Here's a really good question. What happens if there's air resistance? I want you to talk it over with your partner. Which one's going to be greater if there is air resistance? So what do you guys think? So which would have a greater speed, Alice's or Bill's? Alice's would have a greater speed, and that's correct. Why? Well, and this is kind of difficult to think about, but consider this. If there's air resistance, will it ever reach the same symmetrical speed on the way down? No. That speed, when it hits the zero displacement point, meaning when it gets to the point where Alice threw hers down, is going to be less than the speed that Alice threw hers down. Why? Because there's, from the standpoint of energy, which we haven't gotten to, but energy gets dissipated as heat when you throw something up and there's air resistance. As a result, yes. As a result, it basically, as a result, it's going to lose energy, and so that'll never get recovered. Yes? Their velocities are opposites, but their speeds are the same because it's the absolute value. Be a little careful, because now we're instantaneous. We're only dealing with instantaneous speeds. So instantaneous speed is going to equal what? The absolute value of the instantaneous velocity. Or another way to think about speed in a slightly more general way is to think about in terms of the square of the velocity. Because if you take something and square it, whether it's positive or negative, what happens? It makes it positive. So one way to think about it is like this, that the speed squared is equal to the velocity squared. And so, in other words, the instantaneous speed squared is equal to the velocity squared. And why am I talking about squares? Which kinematic equation has squares in it? The second one. So in other words, when I look at this, I think of these terms as speed squares. And you'll see as time goes on, we're going to learn how to work with squared quantities very, very well. And we're not going to square root things. So, all right, so rubber balls. You toss a ball straight up in the air and catch it again. Right after it leaves your hand and before you catch it, what's the V versus T graph? 15 seconds. Very good. 5, 4, 3, 2. Chris, Brian. I know I'm putting you guys under pressure, but that's okay. The whole point is to get you to start thinking under pressure. The answer is 4. That's right. And the reason why it's 4 is because it starts off positive. When it's at its maximum height, it is 0, and then it goes down, which means it's in the negative territory. You drop a very bouncy rubber ball. Okay. It falls, hits the floor, and then bounces right back up to you. What's the V versus T graph? 30 seconds. Remember to each of you individually do your charts, your graphs. Make sure you label them all. Make sure they have units. Make sure your slopes have units. And your intercepts have units. And bring them in, yes. Yeah, print them out, bring them in individually. The graphs. The lab, the actual lab's happening in class tomorrow. The graphs are due tomorrow. You need to bring them in for your lab, and then you need to hand those in. V versus T mid, X versus T squared, X versus T. All right. 5, 4, 3, 2, time. Let me lock it, show you the responses. Most people picked B. So, does anybody have a critique of B? Yes. Put it into words. The answer is D. Take a look. Which way is it going? Down, which means it's going to be the furthest down right before it hits the ground. And then what happens? And then it shoots back up with the greatest velocity. In other words, there's a discontinuity. Correct. In other words, its speed is greatest here and here, right before and after it hits the ground. Yes. Tomorrow, Tuesday, I'm staying after school. So definitely come by for help, especially on the web assignment, which is due tomorrow night. Yes.
Should we just get one copy per group, or should we?
No, each person.